For this one, we have a 2D collision between a fly and a frog. So I'll say that first one's a fly, the other one's a frog. And so the fly is traveling at a speed of v. The frog then is going to leap through the air with a speed of v over 3, and it's going to catch it and eat it. Okay, and we know that the frog has 9 times as much mass as the fly, so I'll say the frog is 9m and the fly is m. And then the two objects, the m and the 9m, are going to move off together at some speed, and that's what we're ultimately looking for. So in order to do this, we're going to set up conservation momentum in both the x and y directions. Initially, the fly, which I'll call object 1, is the only thing moving in the x direction because the frog doesn't have any initial velocity in the x. Afterwards, the two objects are going to move together, m1 and m2, times their final velocity in the x direction only, and that's going to be this component of their final velocity shown there. So we can go ahead and plug in the things we know. The fly is a mass of m, is moving at a speed of v. Afterwards, we're going to have m plus 9m times vfx. We can go ahead and combine this, so we get mv equals 10mvfx. The m's cancel out here, and so what we're left with is our final velocity in the x direction is going to be v over 10. Now in the y direction, the only thing moving before the collision is object 2, which is the frog. And so for that, we're going to have m2v2. Afterwards, the two objects stick together, of course. So it's going to be m1 plus m2 times their final velocity in the y direction, which is going to be that component of the velocity going up. We can plug in the things we know, so we have 9m times the velocity of the frog, which is v over 3. That's going to be equal to m plus 9m times v final in the y direction. We can simplify this sum, and so we end up getting 3mv equals 10mvfy. The m's cancel out here. And we end up getting there, our final y velocity is going to be 3/10 v. We're now going to go ahead and put these components together. So we have our x component, which is v over 10, our y component, which is 3/10 v, and we're going to go ahead and find the magnitude of that overall velocity by doing the Pythagorean theorem here. And so we have v over 10 squared plus 3/10 v, which is really 3v over 10 squared equals c squared. When we combine that, we get v squared over 100 plus 9v squared over 100 equals c squared. That combines to be 10v squared over 100. I'm going to cancel out one of the zeros here by dividing both top and bottom by 10, take the square root of both sides, and what I end up getting is that c is equal to the square root of v squared over 10, or c is equal to v over the square root of 10, which I realize is an improper fraction with the root on the bottom, but that's okay. Either one of those would be an acceptable answer. So for this next one, we're going to go ahead and look at this collision here between two bowling balls with equal mass. We see bowling ball A is moving to the right at a speed of 3v before the collision, and B is moving up at a speed of 2v. In order to solve this one, we're going to set up conservation momentum in both the x and the y direction. I'm going to start here with the x direction. So in the x direction, before the collision, only bowling ball A has momentum because bowling ball B is moving in the y direction. Afterwards, only bowling ball B is going to have momentum in the x because we see that A is moving just straight up afterwards. Okay, and so I'm just going to say the mass of B times the velocity of B in the x after the collision. So I can go ahead and plug in the things that I know. I know the mass of both of them is m. I know that A has a speed of 3v before the collision. B also has a mass of m since they're identical, and so I can solve for the x velocity of B afterwards by canceling out those m's, and I just get that vb in the x direction, the x component of its velocity afterwards, is 3v. We also want to set up conservation of momentum in the y. So initially in the y direction, I just have bowling ball B is moving because bowling ball A is moving purely in the x before the collision. Afterwards, we're going to have bowling ball A is moving in the y direction. So I'll add its y velocity there, and then we're also going to have bowling ball B moving in the y direction after the collision. We can plug in the things we know here, so initially it's just m for bowling ball B times its speed, which is 2v. Afterwards, we have the mass of A times its speed, which is just v, plus the mass of bowling ball B times its y velocity, vby there. I can go ahead and cancel out my m's, and I can solve for vby, and I find that vby is just going to be equal to v. I'm now going to go ahead and combine those two components to get the overall magnitude of my velocity and the angle. So I know that this x component is 3v and it's positive, so it's going to the right. My y component is v and it's also positive, so it's going to the right as well. So I can go ahead and solve for that magnitude doing the Pythagorean theorem. A squared plus b squared equals c squared. So I have 3v squared plus v squared equals c squared. I ultimately get 10v squared equals c squared, which means that c, that hypotenuse, is going to be the square root of 10v squared, or I could pull out that v, and it would just be the square root of 10 times v, with v outside the root. In order to get my angle, I'm going to use tangent, so I'm going to say tangent of theta equals the opposite over the adjacent. I'm going to plug in those values there. So for this triangle, it's going to be v over 3v. Our v's here will cancel out, so that means that tangent of theta is equal to 1/3, and I can take the inverse tangent of both sides of this equation and end up getting that theta is going to be equal to 18.4 degrees north of east. Now, depending on how you set it up, if you flipped your triangle and went north first and then east, you would get an answer here of 71.6 degrees east of north. So either one of those answers is acceptable for your angle. For this problem, we have a firecracker that's initially at rest and explodes into two pieces. So one piece has a mass of m, the other has a mass of 2m, and after the explosion here, they're going to be moving in opposite directions. And so we want to figure out what is the velocity of each one of those pieces. So the first thing I'm going to set up here is conservation of momentum. I know that momentum is going to be conserved in this case. So initially, there is no momentum in my system because nothing is moving, so I can say 0 equals the mass of object 1 times its final velocity plus the mass of object 2 times its final velocity. I'll substitute in what I know, so the one mass is just going to be m, and I'm going to call its final velocity just v1, plus the other mass, which is 2m, and its final velocity is just going to be v2. I can cancel out my m's here, and so my equation becomes 0 equals v1 plus 2v2, or I could say that v1 is just negative 2v2. The other thing I want to think about here is my energy. So this obviously is not an elastic situation because we go from not moving to having energy. So we clearly gain energy here. But I do know how much energy is gained, and it's this amount here, E. So that's going to end up being my work being done. So I can think about my energy in this case. So my initial energy is 0 plus some amount of work being done, which we're calling E. And that's going to be equal to the kinetic energy of object 1 plus the kinetic energy of object 2 after the explosion. So I can use my formula for kinetic energy and what I know about each object, and I can rewrite this equation as E equals 1/2 m, the mass of object 1, times v1 squared, its velocity afterwards, plus 1/2 times 2m times v2 squared. And what I'm going to go ahead and do are two things. Number one, the 1/2 and the 2 cancel each other out. And then I'm going to take this v1 here, and I'm going to substitute it into that equation and combine those two equations. So what I end up getting is that E equals 1/2 m times negative 2v2, that quantity squared, plus m times v2 squared. And when I go ahead and square that quantity, it ends up being 1/2 times m times 4v2 squared. The negative goes away because we've squared it. And now I can go ahead and combine those two equations. This ends up being 2mv2 squared plus mv2 squared. So E is going to be equal to 3mv2 squared. And if I solve for velocity 2, I'm going to divide both sides by 3m and take the square root, and I get the velocity 2. It's just going to be that energy over 3m, the square root of that quantity. Now that I have that, I can plug it back into this equation here that v1 equals negative 2 times v2. So 2 times the square root of e over 3m. And I end up getting my solution to v1. Now it does specify magnitude, so I'm going to ignore that negative sign and just say that the magnitude of v1 is 2 times the square root of e over 3m. For this next one, we have box 1 here, which has a mass of m and is initially traveling to the right at a speed of v. It's going to collide with box 2, which has some unknown mass, so I'm just going to call it m2, and is initially at rest here. After the collision, we know that box 1, the one with a mass of m, rebounds at a speed of v over 2, and box 2 then is going to start moving, but we don't know the velocity of box 2 afterwards. So we want to go ahead and find the mass and velocity of box 2 after the collision. What I'm going to do is set up conservation of momentum and conservation of energy, because I know here that this is an elastic collision. So first thing I'm going to set up is conservation of momentum. Momentum initial equals momentum final. Before the collision, I have the momentum of object 1, m1 v1. Afterwards, both objects are moving, m1 v1f plus m2 v2f, so they both have momentum. I can go ahead and plug in the things I know for these two collisions. So initially it's just going to be mv, because v is the initial velocity of box 1. Afterwards, box 1 rebounds at a speed of v over 2, so I'm going to make that a negative v over 2, plus object 2's mass times the final velocity of object 2 after the collision. I can combine these two terms here because it's mv and really negative mv over 2. So I'll add mv over 2 to the other side and end up getting 3 halves mv equals m2 v2f. So the other thing I'm going to do here is set up my energy equation. So initially we have object 1 has some amount of energy. There is no work being done since the collision is elastic. And then afterwards I'm going to have the final kinetic energy of object 1 plus the kinetic energy of object 2. I can go ahead and plug in what I know here. So the initial kinetic energy of 1 is going to be 1/2 mv squared. That's going to be equal to 1/2 m times this negative v over 2 squared, although the negative sign won't matter since we square it, plus the kinetic energy of object 2, which is just going to be m2 times v2f squared. I can cancel out the 1/2 here, and I end up getting mv squared equals mv squared over 4 plus m2 v2f squared. I'll combine these two terms here, and so it ends up becoming 3mv squared over 4, or 3/4 mv squared, is equal to m2 v2f squared. There's a few ways to solve this. We just need to combine these two equations. What I'm going to do here is divide them, because when I divide this one by this one, a lot of things are going to end up canceling out. So we're going to have 3mv squared over 4, which is equal to m2 v2f squared. I'm going to divide that one side by 3/2 mv, and the other side by m2 v2f. Okay, and then what's going to end up happening is the m's are going to cancel. One of the v's is going to cancel on both sides. On the other side, the m2's cancel. One of the v2f's cancel. And what I'm left with is 3/4 v over 3/2 is equal to v2f. I'm going to multiply by the reciprocal here. So dividing by 3/2 is really the same thing as multiplying by 2/3. And what I end up getting there, because the 3's cancel out, is that 1/2 v equals v2f. Now that I have that, I'm going to go ahead and substitute that back into this equation for my momentum that I had up here. And so 3 halves mv is going to be equal to m2 times 1 half v. The v's end up canceling out. The 2's on the bottom end up canceling out. And I find that 3m is just equal to m2. So here's my answer to part A. My answer to part B I actually had already found, which was that 1 half v. So all that's left to do here is explain part C, which asks about box 1, and we want to explain why the rebound velocity of box 1 must be less than v. And the easiest way to think about this is that when box 1 rebounds, all right, it experiences a change in momentum, and that means that box 2 has to begin moving. Okay, and if box 2 is moving, it has kinetic energy, which means that box 1 must have less kinetic energy than it had initially, all right, in order for energy to be conserved. Okay, so the key point is that box 2 must move in order for momentum to be conserved, and if box 2 is moving, that means it has kinetic energy, so box 1 must have less kinetic energy than what it started with.